kung meron kayong ano, 1, okay, or zero integration factors in the in the forward path, okay, then what would happen is hindi lahat nung S na to, okay, hindi lahat nung S na to makakancel. Okay. So may iwang S sa numerator. What would happen is that kapag in-evaluate yung limit, yung product na to magiging 0. Okay. So kung magiging 0 siya, that means yung denominator nito 0. So 2a over 0. That leads to an infinite error. Okay. That should lead to an infinite error para sa inyong parabolic input. Okay. So again, ito yung tatlong possible values na makukuha ninyo kapag ka in-evaluate nyo yung inyong pag in-evaluate nyo yung ano nyo, yung error ninyo for a parabolic input. Okay? So, ayan. So, let us have an example para mas malinaw nating para mas malinaw natin yung paggamit ng formula natin. Okay. So, again, ayun, nakasunod na wala yung formula dito. Okay, so let's find the steady state error. Okay, for inputs 5u of t, 5t u of t, and 5t square u of t for the system below or for the system. Okay, so again, naka unity feedback system na to. So yung ating g, okay, is basically 120 times s plus 2 over s plus 3 times s plus 4. Okay. So we can verify if this system is stable by determining whether all of the poles are in the left half plane. So you can either use Routh-Hurwitz criterion. Okay, o kaya pwede natin siyang gamitan ng computational software natin. So subukan natin. Okay, so take note na yung system natin, yung open loop transfer function natin or yung forward transfer function natin has 0 at negative 2. Okay. Meron siyang 0 sa negative 2. So, ayun. Gagamitin ko yung ZPK way of defining models. So, kailangan ko yung zeros niya, yung poles niya, at saka yung gain. Okay. So, in this case, makikita natin na may 0 siya sa negative 2. Meron siyang poles sa negative 3 at negative 4. Tapos, meron siyang gain na 120. Okay. So, since kailangan kong hanapin yung closed loop transfer function, I'll use the function feedback. Pero yung feedback transfer function niya is basically 1. Okay, dahil nga unity feedback system siya. Then, ko-computing ko yung poles niya. Okay, so executing that command. We will have two poles at negative 2.0163 and negative 124.49837. So, which means, yung dalawa kong poles ay dalawang real poles at pareho siyang negative. So, lahat ng poles ko nasa left half plane. Okay, so we can deem that this system is stable. So, we can proceed. Okay. So, we can proceed by computing yung error niya due to the steady state, due to the step input. Okay. By using formula ng I think this is 6.11. Okay. So, ito ay 6.11, 6.12, tsaka 6.13. Okay. So, we also take note na yung system ninyo has 0 integration factor. Wala siyang integration factor. Okay. So, from there, okay, we can say na ang steady state error nyo para sa step input would be finite. Okay, again, para sa step input, okay, pag 0 pag ang number of integration factor nyo ay 0, okay, asahan natin na finite yung makukuha. Ito, pag yung number of integration factor natin ay 0, asahan natin na finite yung steady state error na makukuha natin para sa step input. Okay, para sa ramp input, kapag ang integration factor ninyo ay 0, infinite error yung aasahan natin. Okay, ganoon din sa parabolic input. Kapag 0 yung nakuha yung integration factor natin, okay, infinite din yung error na makukuha natin. So, verify natin siya. Okay. So, what would happen is Actually, maganda kasi dito, evaluate nyo muna yung limit ng g as s approaches 0. Okay, so yung g natin ito. So that becomes the limit of 120 times s plus 2 over s plus 3 times s plus 4. Okay, as s approaches 0. Okay, so since wala naman tayong s na factor either sa numerator or denominator, we can simply substitute s 0 dun sa s natin. So that should become 120 times 2 divided by 3 times 4. Okay, so that should become I think this is 12. Tapos this is kung 12 yan, magiging 10 to. So 20. Okay, so that should become 20. Yung ating DC gain. Okay. So yung kung ito ay 20, so ito ngayon magiging 20 siya. Okay, that means also that yung error natin for the step input or yung error natin due to the step input should be a finite error. Okay, so that amounts to 5 over 21 pagka kinompute natin. Okay, so that's 5 over 21. Mamaya i-verify natin yan. Okay. Now, for the ramp input, let us first compute yung denominator. Okay, actually yung denominator yung unang kino-compute sa mga ganito para mas makita nyo siya. Okay, and later on, sa next lesson, magkakaroon tayo ng special name sa denominator na yan. Okay, so we have the limit of SG as S approaches 0. So this is the limit of S times 120 S plus 2 over S plus 3 times S plus 4 as S approaches 0. Now again, dahil nga sa absence ng integration factor doon sa G ninyo, walang magka-cancel sa S na to. Okay, hindi makaka-cancel tong S na to. So what would happen? Kapag synapse or kapag in-evaluate ko yung limit na yan, automatic, ito, magsisiro lahat yan. Kasi may 0 kayo times ito. So 0 times ito, automatic 0 yan. So ngayon, kapag synapse ko yung 0 dun sa formula ng 6.12, okay, that should give me 5 over 0. So again, that should approach infinity. So that confirms yung diniscuss natin kanina that kapag wala kayong integration factor for a ramp input, magi infinite yung error. Okay? And finally, para dito, compute natin yung denominator which is s squared g as s approaches 0. So that should become the limit of s times 120 s plus 2 over s plus 3 times s plus 4. Okay, as s squared to, no? As s approaches 0. Okay, again, in the absence of integration factor, hindi maka-cancel to, yung s squared dito. So that pag in-evaluate nyo yung limit na yan, that entirely becomes 0. So therefore ito, magkakaroon ka ngayon ng dito, ng denominator na 0. So this becomes 10 over 0. Again, this is 2a. Okay, actually yun yung pinagkaiba doon sa ibang formula. So dito, magagamit itong 5 at saka 5 na to dun sa pag-evaluate ng steady state error para sa step at saka sa ramp. Pero sa parabolic input, yung kanyang amplitude or yung kanyang that's the acceleration kasi. Okay, that's the acceleration. Okay, so yung 5 na yan, that's the acceleration. Idodoblehin natin yan. Gagawin natin yan 10. Okay. Although what would happen is that dahil nga apektado siya ng division by 0, still your error becomes infinite. Okay. So ayun, that is in the absence of an integration factor para sa system niyo or para sa open loop transfer function niyo. Okay. So that's example 6.2. Okay. Sa example 6.3 naman, meron na kayong isang integration factor. Okay. So, again, kung meron kayong isang integration factor, para sa step, okay, you would have, so isang integration factor, no? N equals 1. Okay, para sa step, meron kayong 0 error. So, i-recall nyo kanina na pagka meron kayong isang integration factor, meron kayong 0 error para sa step input. Meron kayong finite error para sa ramp input. Tapos meron kayong infinite error para sa parabolic input. Okay, so verify natin verify natin kung stable siya. Okay. So, ayan. So in this case, we will have yung ating zeros as at -2 at saka -6. Okay. Yung ating poles at the origin kasi may isa kayong integration factor. Tapos meron kayong pole sa -3 at saka sa -4. Tapos meron kayong gain na 100. Again, para maging closed loop to dahil nga siya ay unity feedback system. So para maging closed loop pole siya or closed loop system siya, gamitin natin ng function ng feedback. Okay, and then let's compute for the pole. Okay. So yung closed loop poles nung system at located at negative 0.9 o 6.1. So lahat yan ay real poles pero lahat negative. So we can conclude na lahat ng poles nyo nasa left half plane and therefore your closed loop system is stable. Okay, so we can proceed now with the use of the formula nung ating Okay, so again, this is equation 6.11, 6.12 at saka 6.13. Okay. So again, ang kukumpitin muna natin is yung denominator or yung DC gain in the case nitong steady state error para sa step input. That's the limit of g of s as s approaches 0. Okay, so this is the limit of 100 times s plus 2 times s plus 6 over s times s plus 3 times s plus 4 as s approaches 0. So what would happen is that kapag in-apply ko tong limit na to, isa-substitute ko yung 0 dun sa s. So that should become 100 times 2 times 6 divided by ito, magiging 0 yan. So times 3 times 4. Since ang denominator nito is 0, okay, so clearly, itong ratio nyo na to actually becomes an infinite number. It becomes very large. Okay, it becomes very large. So what would happen is kapag sinubstitute natin siya ngayon dun sa inyong 6.11, okay, that becomes 5 over 1 plus an infinite number is still an infinite number. Okay, so yung 5 over a very large number is 0. So that is why magkakaroon ka talaga ng 0 error para sa step input. Okay, now in the case ng ramp input, this is yung denominator niyan, okay, is the limit of s times g. Okay, as s approaches 0. So this is the limit of s times 100 times s plus 2 times s plus 6, okay, divided by s times s plus 3 times s plus 4. Okay, as s approaches 0. Ngayon ito at saka ito magka-cancel yan. So that is why pag in-apply ko yung limit, that becomes 100 times 2 times 6 divided by 3 times 4. So clearly, finite number to kasi wala kayong 0 dito or wala kayong 0 sa numerator. So ito tsaka to magka-cancel. That becomes 100. Okay, so that should give you an error na 5 over 100 or 120. So again, that verifies na kapag meron kayong isang integration factor, okay, yung error nyo due to a ramp input is finite. So in this case, this is 1 over 20. Okay, finally, para sa parabolic input natin. Okay, para sa parabolic input natin. So we first compute the limit of s squared g as s approaches 0. Okay, so this is the limit of s squared times 100 times s plus 2 times s plus 6 divided by s times s plus 3 times s plus 4 as s approaches 0. Okay, so what would happen is ito at saka to magka-cancel. Pero may iwan pang s sa numerator. So that is why kapag ito or in-apply ko yung limit dito, that should become 0 times 100 times 2 times 6 divided by 3 times 4, which is clearly 0. Okay. Kaya ngayon, pag itong 0 na to, sinubstitute ko doon sa denominator ng 6.13 kasi nasa denominator siya. That is 2 times 5, 10, divided by 0. That should become infinite. So, kapag meron kayong isang integration factor, again, yung parabolic input ninyo gives an infinite, error. Okay? So, ganito gawin natin ngayon. Balikan natin yung example 6.2. Tapos tingnan natin kung paano yung error niya. Okay, paano yung error niya in terms ng paano yung error niya in terms ng simulation. Okay. So, this is a possible itong part na to. Okay, this is a possible these are possible commands na pwede nyo gamitin para ma-evaluate yung steady state error nung nito. Okay, nung system na to para sa para sa sa step input. Okay, so again, dinefine natin yung system natin using ZPK. Okay, so meron siyang 0 sa 2 sa negative 2. Okay, meron siyang 0 sa negative 2. Tapos meron siyang pose sa negative 3, negative 4, meron siyang gain na 120. Okay, so then in-evaluate natin yung closed loop transfer function T. Okay, so ito yung ginamit natin para malaman kung stable yung system natin o hindi. Now, at this point, gagawin ko, mag-i-input ako sa kanya ng step signal. Okay. Pero since gusto ko sana kasi is pare-pareho yung commands na gagamitin natin para sa step, ramp at saka parabolic. Ang iibahin ko lang ito, yung signal na i-input ko sa kanya. So I opted, kahit na step input to, I opted to use LSIM. So LSIM can actually accommodate any types of signal. I-define lang natin yung ating time time vector at saka yung signal natin that corresponds to that time vector. Okay, so nag-define ako ng time vector from 0 hanggang 0.07 seconds. Okay, with an interval of 0.01 in between time points. Itong 0.07 na to, arbitrary to. Okay, kasi actually bago ko i-run ito, tinest ko na yung steady state nung system niyo at nalaman ko na around this time alam ko nakasettle na siya. So para medyo maikli lang yung may konti lang yung time na gagamitin natin. Or maikli lang yung time vector natin. So nilimit ko lang siya sa 0.07. Okay. Tapos gumawa ako ng step signal. So ang step signal natin is basically 5 pala to, no. So kailangan ko pala siyang i-multiply ng 5. Okay. So kasi 5 tapos times yung ones, mag-generate siya ng vector na puro 1. Okay, yung dami nung elements na 1 ay nakadepende sa dito. Okay, so row vector dahil 1 yung first argument. Tapos ito yung number of columns. So yung number of columns na yan, depende kung gaano kahaba ito. So if there are yung T ko has 71 columns. So it means na mag-generate ng 71 na 1. Tapos yung bawat 1 na yun, i-multiply ko ng 5 in accordance dun sa ating input na 5u of t. So ito siya. Okay. So now, I would plot the response, okay, using the command LSIM. So ang sequence nun is yung system niyo, which is t. Yung signal niyo, which is the step input. So S siya sa case na to. Tapos yung t, which is the time vector. Okay, so yung access nyo, nilimit ko lang sa 0 hanggang 0.07. Tapos 0. That's for the x, yung x limits ko, 0. Tapos hanggang 0.07. Okay, tapos sa y is 0 siya sa pinakamababa. Tapos 1.1 sa pinakamataas. Okay, and then, katulad nung ginawa ko kanina sa step function, kinuha ko rin yung data points that would correspond to this one. Okay, and then I would compute the steady state error due to the step input as yung final value nung signal ko, okay, which is Sn, tapos yung final value nung output ko. Okay, yung final value nung output ko, which is Csn. Okay, so i-plot natin siya. So unang-una, i-adjust pala natin to kasi nag-adjust na nga pala ako ng 5 dito. So adjust natin tong axis natin. Gawin natin tong 5.1 instead. Okay, so ayan. So this is now the resulting plot. Okay, this would now be your resulting plot. Okay, so makikita nyo na ang final value kasi ng signal nyo ay 5 kasi 5u of t nga. So yung amplitude ng step signal nyo ay 5. Tapos, ito yung magiging final value ng response nyo. Okay. So, yung final value ng response nyo is so wala peak response. Sige. Kunin natin yung peak response. Anyway, the peak response would be ano. So, the peak amplitude niya is 4.8. Yun na naman yung final value niya. So, yung 4.8 na yun. Okay. So, yung difference between itong final value ng input niyo which is 5, tsaka yung final value nung nung system niyo which is 4.8, yung gap na yon, 5 minus 4.8, yun yung steady state error niyo. Okay, assuming na again nga at this point nakasettle na yung system niyo. So yung nakuha nating 5 minus 4.8 is yung which is 0.2. Okay, that would be your steady state error. Ang nakuha natin dito is basically 5 over 21. Okay, so pag kinompute natin yung 5 over 21, so that's 5 divided by 21. Okay, that's 0.23. So almost malapit na yung error na nakuha natin. Pero actually, itong command na to which I used to compute the numerical or numerically compute the error, that gave me 0.2047. Okay, so sa computation, ito yung nakuha natin. Ito yung nakuha natin sa MATLAB. 0.247. So medyo may discrepancy. Okay, again, ito kasi sa MATLAB natin is numerical yung calculation. Ito naman analytic based dun sa formula na dinerive natin. Okay. So pero nandun yung idea na makukuha natin yung steady state error. Okay. Now, let us try now to do this again pero this time sa ramp naman, sa ramp input. Okay. Now, dito naman, meron naman tayong ramp signal. So, yung input natin is ramp. So, para makapag-define tayo ng ramp, that's simply 5 times the time vector. So, magiging ramp na siya. Okay. So, pinilitan natin yung S nung R kasi R na siya. Okay. So, ayan. Now, yung axis natin is in-adjust ko ng konti. So, kinuha ko siya sa 1 second. Okay. So, ayun, ito yung ating plot. Tapos, okay, ito yung kailangan yung i-take note dito. Unang-una, base sa plot pa lang, okay, makikita nyo na hindi na parallel yung dalawa. Okay, hindi parallel yung dalawa. So, again, kapag hindi parallel yung dalawa, that represents an infinite error. That should represent an infinite error. Recall yung discussion natin doon sa previous lesson. Okay, na pagka yung ninyo, yung output niyo is output 3 which is not parallel dun sa input natin, that results in infinite error. Okay, so now this command may return an output that is halimbawa ito 0.2596. Okay, pero take note na kapag binago ko yung time sabihin natin gawin natin itong 2 seconds. Okay, tapos gawin natin din itong 2 seconds. Okay, tapos niran natin yan. Okay, so still magkakaroon ako ng na hindi nga siya parallel. Okay, hindi pa rin siya parallel. Pero okay, again, nakita nyo na bago yung value niya. Okay. So ito yung sinasabi ko sa inyo na pag nagme-measure kayo ng steady state error at different points in time, tapos hindi parallel yung dalawa yung input nyo tsaka yung output nyo, mag-iiba yung value niyan. Okay, so at the end, pagka mineasure nyo siya in terms ng infinite time, infinite nga yung magiging error niyo. Okay. So tingnan niyo mabuti. Okay, kaya bago kayo mag-compute ng error using this formula. Okay, bago kayo mag-compute ng error using this formula, tingnan niyo mabuti muna yung plot niyo. Okay. At tingnan niyo mabuti kung ano yung pinag-usapan natin nung una regarding dun sa possibilities dun sa dun sa mga inputs niyo. Okay, so in terms ng ramp, tatlo yung possibilities niyo. Pwedeng coincident sila. So yung dalawang lines nyo, yung input nyo tsaka yung yung output niyo magpapatong. Okay, so that means zero yung error niyo. Yung second possibility na parallel sila, hindi sila magkapatong, hindi sila coincident, pero parallel sila. So in that case, finite yung error niyo. Okay? At yung pangatlong case na hindi parallel yung input niyo tsaka yung output niyo. So in that case, that should return an infinite error. Okay, so tingnan din natin ito sa case ng parabolic input. Okay. Okay, so dito, notice na pinalitan natin yung parabolic yung signal niyo as 5t square. Okay. So, yun yung parabolic input natin. So, again, ginamit pa rin natin yung LC. Yung gray still represents the input, blue represents the output. Okay, and pansinin natin na kumbaga, although at this point, hindi masyadong mukhang hindi parallel yung pagkakaparabola ng dalawang curve ninyo. Pero pansinin nyo to. At the end of 2 seconds, ang difference between your two curves is 1.04 or 1.046. Okay. Kung i-extend ko yan at sabihin natin nasa settling na siya, nagsettle na siya at that point, dapat makuha ko rin yung same value na yan kapag in-extend ko yung waveform ko. Okay. So sabihin natin i-extend natin siya say sa 3 seconds. Adjust natin to, say for example, yung upper limit nito kasi 20 ko siya in-adjust 20.1. So gawin natin tong mga 40 siguro. Okay. So and then let's run this one. Okay. So ako lang pa. Ayan. So ayun, hindi pa rin natin kita. Medyo adjust ko pa to ng 50. Ayan, so yun, nakuha natin yung dulo nung Okay. So, dapat, ganoon pa rin yung Pero in this case, hindi kasi. Ibig sabihin, yung gap nila, lumaki pa lalo. Okay. So, yan yung yun yung sinasabi natin na pag yung gap na yon sa dulo nung graph ninyo or ng waveforms ninyo is actually getting bigger and bigger. That means yung error ninyo infinite. Dahil yung gap na yan, pag lumalaki yan, as you actually increase the time, that means at t approaching infinity, that gap becomes infinite. Therefore, yung error ninyo is also infinite. Okay. So, ayun. Now, pakita natin yung case nung 6.3. Pero kung ipapakita ko, sige, pakita natin yung tatlo. Okay. So, again, sa 6.3, yung isa, okay, yung ating is steady state error natin due to the step input is 0. Okay. Tapos dun sa isa is sa ramp is 1/20, tapos ito infinite. Okay, so pakita natin yung tatlong cases na yan. Okay, so in example 6.3, yung ating system has poles, has zeros at -2 at saka -6. Meron siyang zeros sa 0. Meron siyang poles sa 0, -3 at saka -4. Tapos meron siyang gain na 100. So again, kunin natin yung closed loop system or yung closed loop equivalent transfer function. Okay, and nalaman natin kanina na stable siya. Tapos, again, ulitin ko yung ginawa natin kanina sa example 6.2 wherein I define the step input, okay, in terms ng ones function. Okay, pero this time, hinabaan ko yung signal ko or yung time vector ko para ipinaabot ko ng 2 seconds. Okay. Actually, that is after some trial and error. Okay, kasi anong nangyari is that na-discover natin na meron pala tong konting overshoot. So nag-overshoot ng konti, probably because dun sa poles niya. Okay, dahil siguro dun sa poles niya. So medyo underdamped pala tong system niyo. Okay, so medyo in-adjust ko ng konti yung yung simulation time hanggang 2 seconds. Okay, para ma-capture natin yung entire story ng waveform niyo. So that is why it is important na bago kayo mag-report ng results, siguraduhin niyo muna nakasettle siya. Okay. Most especially sa pag-evaluate ng steady state error kapag simulation. Okay, kasi again, ang problema dito is that hindi natin alam kung yung ipinapakita ng MATLAB na graph or yung ino-compute niyang is nagse-settle na ba yung niyo. So lumalabas nga dito na siya na although yung system niyo is basically overdump. Okay, kaya nag-overshoot pa rin siya. Okay, so ayun. Overdump to dahil yung closed loop poles natin. Again, closed loop poles na to yung kinuha natin. Okay, so going back here. So pinaabot na natin ng 2 seconds para masigurado natin na nag-settle na siya. Okay. And again, computing now yung ating steady state error, okay, by subtracting the end value or the final value of your signal, okay, which is basically 5 based dito, and the final value of your output, okay, that should give us a value na ganito. Okay, so more or less malapit na yan sa 0. Again, ang na-evaluate natin using the formula is 0. Okay. Now, let's do the same sa ramp signal. Okay. Okay, so in terms ng ramp signal, pansinin natin na ito siya. Okay, so medyo hindi obvious na parallel siya, no? Okay, pero i-zoom natin siya at a certain point. Okay. I-zoom natin siya. Okay, zoom natin yung natin, yung ating waveform. Halimbawa dito. Okay, so makikita natin na mukhang na parallel siya. Okay, so yan, parallel siya. Okay, so kahit nasundan natin yung waveform ninyo, okay, hanggang sa dulo, we would be able to see na parallel siya. Okay, so another sign na parallel yan is ito. So at 2 seconds, after 2 seconds, ito yung nakukuha yung error. Okay, pwede natin to. Ayan. So at 2 seconds, ito yung nakukuha natin error. Okay, so i-extend natin yung time vector natin sa 3. Okay, so ito, i-extend natin sa 3. Okay, and then likely 15 ito. Okay, so we can see na more or less nandun pa rin yung nyo, yung error niyo. Nandun pa rin sa value na yun, na 0.05. Okay, na 0.05 siya. And in fact, that agrees with with what was computed here, 1/20. Yung 1/20 na yan is basically 1 divided by 20. That's 0.05. Okay, 0.05 yan. So, nag-agree ngayon yung results ng simulation natin. Okay, yung results ng simulation natin, okay, with that of your computation. Okay, so ganyan yung makikita nyo kapag ramp yung ramp yung input. Okay, so ang suggestion ko, pag hindi nyo makita parallel siya, pwede nyo siyang i-zoom. Okay, and again, an indication na you are getting a finite number, a finite error kapag kahit na i-extend nyo tong simulation time nyo to, you would still be getting the same amount of error. So, ayun. Ganun pa rin yung error niya. 0.05 pa rin. Okay. So you may want to use MATLAB para ma-verify nyo rin yung results nitong parabolic input. Okay. Para makita niyo na yun nga yung magiging error niya, which is infinite. Okay. Also, please do work on example 6.4 para ma-practice niyo yung paggamit ng formula. Okay, and at the same time, again, yung dapat maging careful tayo sa pag-apply ng formula sa letter B dahil nga lumalabas yung system niyo ay unstable. Okay, so you may want to verify that condition para sa 6.4, para sa letter B na 6.4 na nga siya, unstable nga siya. So at hindi natin ma-apply yung mga equations natin for the error. Okay, so you may use MATLAB for this one para malaman nyo kung unstable nga siya o hindi. Okay, so ayun.